Well, it's just. So,
All right, guys, let's get started. So we're not going to do too much today. Get through the first section, just remind ourselves where we were, where we left off. We're starting with chapter 13. This will be the last chapter we do in this class. So it's, Arden's a very nice book in that he has a chapter like this, and that similarly, like with isometries of the plane, there's a chapter on that. And these, but so the way he structures his book is instead of just being like the last sections or last chapters, it doesn't work, and then he has a chapter that illustrates it. So this is like, you should think of this chapter as like an application of what we learned with PIDs, UFDs, all of that, some of the rings. So it's not something where it's like, okay, if I don't know this, I'm going to be in trouble with, graduate algebra courses, or if I, whatever. This is a topic, and you can, not like it or like it, but it should get in the way of moving forward if you further. So last time, or last, I don't know, week or something, we studied factorizations. And we've got this kind of picture. Let's try to reorient ourselves. We have these Euclidean domains inside of the world of principal ideal domains. And these are inside of this world of unique factorization domains. And this is in the world of unique domains. So the outer shell is sort of very big, sort of, they take, sizes of the sun versus the earth or something. Like this is a much, much larger world than this. This is a much larger world than this, and so on and so forth. This actually is a very, very small world. So what we're going to do today is see that we can actually, with very simple cases, be in this world. And in fact, this is a very much, what I'm saying is true, that this is a very much larger world than the UFD case. And in fact, sometimes there are only a few UFDs amongst things you're looking at, or type. So what we're going to do is we're going to look at quadratic number fields and their rings of integers. So in order to do that, I need to say a couple of things. What is a number field? Number field is field generated by rationals and some finitely many complex numbers. So it looks like the following thing. Look at the notation would be something like this. Subset or subring or subfield, however you want to take it as Z, if you want to look at it that way. You don't, there's other ways of thinking about it, but so now we're going to start. I mean, what you can start with, and the best thing to start with is to start with just choosing a single alpha. So we'll be looking at the case where we have a single alpha. Okay, so I'm actually lying a little bit here. I don't want to give you the full definition, but actually let me give you the full. Let me not lie. All right. So here I need one condition on the alphas. I want each of these alpha i's to satisfy a polynomial equation in the preceding set of alphas. In other words, there's a polynomial for which alpha I is a root, where the coefficients of that polynomial are in the first, on the field generated here. That's the actual. We're not going to use this, but that's the actual. What we're going to do is we're going to do the case where we just have a single alpha, and then this last bit becomes a little more clearly what I'm saying here. So n is equal to 1, and we're studying Q of alpha, where alpha is a root of a polynomial. Coefficients. Now, one thing we did do last time is we did show this diagram. In particular, if you're looking at this ring, polynomials with rational coefficients, we saw that that's actually a Euclidean domain. Because the degree function is this sort of tells us this Euclidean function that will fit into the division algorithm and so on. What that means is that this is a UFD. And so in particular, if we have alpha as a root of f of x, then we can find an irreducible factor of f of x for which alpha is a root. Is that clear? Let's just make sure. So f of x is going to equal, I don't know, e1 of x. If alpha is a root, then we have 0 is equal to f of alpha, p1 of alpha. So one of these must be 0, right? What I'm trying to say is we can assume then f irreducible. Obviously, if I multiply by a non-zero rational number, that won't affect. In other words, if I say, okay, I've got some element alpha, it's in my complex plane, and there is some polynomial for which it's a root, then I can choose that polynomial to be irreducible in model. Make sense? And of course, when I say irreducible, I mean irreducible in this string. if you look in complex coefficients, the only irreducibles are what kinds of polynomials? That's a question. Sorry. Phrased it with enough emphasis. I mean, I'm trying to make sure that people understand what I'm saying here when I say reducible. If I was in coefficients and complex coefficients, it's irreducible, what kind of polynomial would I have?
Just have x minus some alpha.
Right, I'd have a degree 1 polynomial, because this is the fundamental theorem of algebra. I have a polynomial any degree, then I've got a root, which means I've got x minus alpha. So, however, this is, of course, the fundamental theorem of algebra is not true in this root. There are a lot of irreducible polynomials here. All right. So, in fact, we have a name here. It's called, well, Arden calls it something a little bit different, so I'm not sure I want to, but I'll call it what it is called. So in this case, f of x called minimal polynomial of, and Arden calls it the irreducible polynomial. I'm not sure about that. Maybe it's a number. Okay. So what we can do is we can kind of understand these rings, understand these fields by understanding these polynomials, at least to some degree. Now, I want to define a couple more things. One is an algebraic integer. Okay. An algebraic integer alpha. Well, it's a right number means some element of C, which is a root of a polynomial with coefficients in Q. Minimal polynomial has integer coefficients. So what is this dance we're doing here? The idea is fields are very interesting, and sadly, we're not going to have a lot of time to talk about field theory in this class. There's a lot you can say about fields. However, as rings, they're not, they're sort of boring in a sense. Like by themselves, if you study the ring theory of a field, there's not much to say. However, rings are very interesting if you study rings. And so what you can do is it turns out that if I have a field like this, I can look inside of it and I'll look at the algebraic integers that live inside of here. That forms an interesting ring. And studying that ring leads to a lot of interesting mathematics. That's essentially the subject. I mean, the very small version of that is the subject of this. This is kind of the larger picture of what we're looking So now this is one definition. Another. A quadratic number field. Field. Form u square root d. Some and you probably want d to not be a square. I mean, if d is a square, it's just a square. Okay. So first task is to take a quadratic number field and find its algebraic integers. So in order to do that, we want to kind of get a sense of what we're dealing with. We have one of these. Oops. Elements. E are the form A plus A and B are rational. One thing to note. Other thing to note is that you may assume D is squared for E. People assume that. In other words, there's a factor of 4 or 9 or something. We can just take that out because it will just come out. There's a little notation, and we're going to focus on one side, I think, most of the chapter, which is that we can consider two different cases, so two main cases. One is that D is positive, the other is D is negative. If it's positive, we say this is a real quadratic field. Otherwise, we call it imaginary. So we're going to focus mostly on this case. So it's sort of the easier case in a sense. But not really. We'll get to it. One more thing. So yeah, okay. So now, why do we call it a quadratic number field? So let's say we have this as alpha. So we call it quadratic number field because the minimal polynomial of alpha, as a complex number, is going to be quadratic. For any alpha, but certainly square root of d. The minimal polynomial here we're assuming b. In other words, assuming that d is not a square. Of course, d is a square, which is that direction. And assuming b and b is not zero. how do we get it? Suggestions? How can we get a minimal polynomial? So, I think you've probably done this before. I'm guessing at some point in your life doing calculus. Guess these kinds of questions.
Like conjugate it basically.
Yeah, it's like a conjugation. We just take x minus alpha. I'll write it out. X minus. Let me just put a negative here. And you're going to get 2a x squared 2a plus a squared they have these weird, I mean, you may not recognize this from calculus, but there's like some weird, they'll have some limit thing, and they'll put like something on the numerator. The trick is to conjugate. Okay. So if you see, if A, B, and D are, well, D is an integer, but A and B are rational, so this is a rational number, and this coefficient here is also rational. So indeed, this is in the rational polynomial, and it's monic. Leading coefficient is 1. So this must be, well, this is a polynomial that has alpha as a root. But why is it the minimal? Well, the point is there's no linear polynomial for which alpha is a root, because it would look like this. But we're assuming that this is not in rational. This is not actually a polynomial in here. So there's no factors. Questions? So now what we want to do is we want to say, okay, well, what happens? Can we find the algebraic integers here? So let's say we look at this field, we find the algebraic. We need some kind of which is not really, I mean, a lot of these lemmas are kind of just, I think, basic, but okay. Let's let D be for 3. Are rational. R squared D integer R squared.
Would it be because if you square
So good. So, right, if I take, so let's write it out, say R equals A over B. And R squared D equal A squared B squared times D. And yeah, and then the point is that here we have two, we have two prime factors for every prime factor of B. And we can assume A and B are relatively prime, so none of the factors here divide here. So they all have to divide B, but then we have square factors of D. D is square free. We can't do that. Too many factors of B squared. Say that. I mean, this is really just an appeal to the fundamental theorem of arithmetic. We have prime factors. Okay, so but we're going to use this and to find these algebraic integers. Here's our proposition. And then we'll see, like, this actually gives us kind of a pretty nice picture. It's a measure. All right, so the algebraic integers of the quadratic field Q D E squared free have the form A plus BI. Sorry, I square root B. Where so either D is congruent to 2 or 3, not 4. A and B are both integers. Or D is congruent to 1 mod 4. A and B are both either half integers with half integers, so they look like 8 plus 1 half, or they're both integers. And the comment is that then the algebraic integers, which is the thing we want to study actually, okay, the algebraic integers from a ring. Ring of integers, so-called, this is a definition. Ring of integers. Okay. Let's prove this. So one thing we know is we know in order for us to have an algebraic integer, we know that these coefficients, which are the coefficients of the minimal polynomial of alpha, must be integers. That's the definition. So we know that 2a and a squared minus b squared d are both integers. 2a, b squared minus b squared d, these are integers. If and only. If and only. Now, if a is an integer, which is certainly possible. I mean, either a is an integer or a is a half integer, right? Because 2a is an integer. Nothing over 2, or it's an integer. If a is an integer, though, then well, because this whole thing is an integer, we can subtract a squared, and we get that b squared d is an integer. If that's the case, then we have this lemma that we just said. That means that b is an integer. So what I'm saying is if if a is an integer, then b has to be an integer too. Then we get both of them right. If a is not an integer, then it's a half. Then we can say, okay, well then it's a half. So a is equal to a tilde plus 1. Some a tilde. So now let's square it. So a tilde squared plus a tilde plus 1/4. Now we know that this has to be an integer in order for us to be an alpha to be an algebraic integer. So b squared d, this is an element d plus 1. Yeah.
The statement, if a is an integer, then b squared is that relationship.
So it happens here. So that part, it happens here. A is an integer. So what we have is we have a squared minus b squared d is equal to some integer c. So if a is an integer, then I can just rearrange it. B squared d equals a squared minus. Sorry, it's a squared minus c. These are both integers, so we get that this is an integer. So that's okay. Here, here everything's okay, but I think maybe it'd be better if I did it like I'm doing it. That way I don't do it. Let me do that. So what we get is and so b squared d, it's still going to be a squared minus c, but here we'll have like something like a tilde squared plus a. So we get something, we get an integer of plus 1. That's what I'm trying to get. And now we can, point is we can multiply everything by 4. D squared d Now, this is an integer. This is equal to 2b. Now we have that this lemma that said that if I have a rational times an integer, a rational squared times an integer, then that rational has to be an integer. Again, by lemma, 2b is an integer. Now, what we want to conclude is that that in order for this case to occur, not only is 2b an integer, but then b itself has to be congruent to 1. Mod 4. Also want so b is equal to b tilde 2. And what can we say? Then I want to say b squared d is an element for only a b tilde, sorry, d. Okay, so now the question is, well, this actually is not, this is where argument sort of stops. But I want to verify. Let's say why this is true. What we're trying to prove, what we have, let's summarize what we said so far. Which is that we certainly know that alpha is algebraic integer if and only if these two are integers. In the case that a is an integer, we get that b is an integer. And conversely, that's also, if b is an integer, then a also has to be. Okay, if a is an integer, then we get that indeed b is an integer. Now suppose a is not an integer. It's of this type. Then we get that b is also of that type. B is b tilde divided by 2. Now we want to say that, okay, this is only going to happen if d is congruent to 1 level. It can't happen if d is congruent to 2. Why is that? I did introduce some notation. Why is d congruent to 1? This equation. So what, so are you, what are you saying? Say it again. I couldn't quite hear you.
Sorry, so, is, up to the player, and, if you square that when you get four squares, then, oh, never mind. Never mind.
I think you said something mod 4, but I like. So this is an equation in integers. So that the problem here is where are the rationals and where are the integers? So if we look at B, B is not an integer. B is a rational. So, and then we concluded by this lemma that B is a fairly easy to understand rational number. It's some integer divided by 2. We got some expression here, but now when we look at it this way, here B tilde, that is an integer. So is D, and so are all of these guys. So I have an equation in integers. And I can, yeah,
Like that 4 times stuff is going to be 0 mod 4. So +1 makes it 1 mod 4. And you can multiply anything. If it's 1, you can multiply by anything.
well, let's just take what you're saying. This is, I can write this, because it's an integer equation, I can write it as an equation mod 4. Get this equation mod 4. Now, I'll ask you guys, what about B tilde? What could it be? What do we have mod 4? What are the possibilities? 0, 1, 2, and 3, right? So 0, can B tilde be 0? No, because this would be 0. B tilde be 2. So there's 2, we get 0 again. I mean, this would be 0. So B tilde can't be 0 or 2, which by incidentally means that B tilde in this case is odd. So we do indeed get a fraction. What about B tilde equaling 3? Sure, why not? But what is 3 squared? Mod 4. 1. Right? So in that case, it's 1, and when B tilde is 1, it's also 1. So what this is saying is there are 2 cases, 0 and 2, which don't happen. And the cases that do happen, when B tilde is 1 or 3, we get D is congruent to 1. Both times. All right, good. And that gives us that problem. So now, of course, D could be congruent to 2 or 3. And in those cases, we don't have this case where A has to be an integer. So why is this kind of a nice thing to understand? Well, it does give a picture, and Arden has a couple of nice pictures here of the algebraic integers. So first, let's look at, let's restrict our case, and I think we do this for the rest of the chapter. I'm not sure, but I will restrict to the imaginary case. 0. Here we're looking at this guy. Inside of here, we have this guy, algebraic integers. Now we get a picture. Maybe we didn't have it. These are elements of the complex plane. And we have the integers. Yeah, the worst, I don't, necessary. So we have 2 cases. We have D congruent to 1 or 2, Sorry, 2 or 3, pardon me. 2 or 3 mod 4. In this case, we just had integers. A and B were integers. So algebraic integers, A. What does that mean? Well, it means here I can look, I've got my ordinary integers, which I'll space out by like 2s. This is on my real line. And then I've got, well, I've got things that look like A, this is A, plus B times the square root of D. The square root of D is negative. So it's this is the square root of absolute value of D times I. Here, the square root of D is equal to I times square root of value. So what we've got is we've got some number here, some complex number. I don't know, it's very irrational looking. And we're just kind of going up in that number. And everything is sort of like, multiples of that. Bring it over. So on and so forth. So we get some rectangular lattice here. The ring of integers. On the other hand, oh, I mean, this thing, of course, will repeat. If you try to do this for D, I mean, you don't try to do this. If you look at the same kind of picture for the decongruent to 1 case, here we know that we also have so we do have integers, but we also have the case of the square root. We have A and B are half integers as well. We'll get this kind of a picture, but we'll also get some picture where you can take the thing and we'll see something sort of in the middle. We're kind of moving up halfway. So we'll get this, he calls this an isosceles triangle kind of. These are the two pictures that so indeed we do get lattices for the rings of integers, and studying those lattices can be used in tandem with studying the arithmetic of these rings. That's what we'll do